AI is doing incredible things, from generating artwork to animating photos to answering almost any questions you throw at it. But when it comes to applying AI in real-world business scenarios, there's still a big problem: reliability. AI doesn't know when it doesn't know. Traditional AI models can't recognize the limits of their own knowledge. They often give confident answers even when they are completely wrong. You can ask a large language model something like, "How do living people talk to the dead?" And it might give you a logical sounding answer that's totally made up. Not because it's doing that on purpose, but because it doesn't know how to say, "I don't know." This isn't just a weird side effect. It's a fundamental risk for using AI in business, because companies can't afford to act on guesses. So, why do this problem matters? Because unreliability limits AI's adoption. Even if an AI model is powerful, business won't trust or deploy it if they can't rely on its responses. Let's look at why that matters. In business risk, wrong answers lead to financial loss, safety issues, or logical exposure. If people can't trust AI outputs, they will double-check everything, which defeats the purpose. Especially in regulatory barriers. In sectors like healthcare, defense, and finance, explainability and confidence aren't optional, they are required. And you can't automate decisions if the system needs constant human babysitting. So, here are the opportunities. If we solve this, if models can reliably say, "I don't know," when they are uncertain, it could unlock the next generation of safe, scalable AI. So, which means solving the unreliability problem doesn't just reduce risk, it makes AI 10 times more valuable to the enterprise. How that happened? More departments can safely adopt AI, from compliance to customer service. Less human supervision means faster, cheaper automation. And critical side using cases open up. Fraud detection, mental trigger, autonomous driving, and more other business scenarios. Users get confidence with this, and it leading to broader adoption. Also, AI teams can finally focus on retraining efforts what they are most needed. Before we go deeper into the reliability problem with AI, let me introduce the star of the day, Themis AI. Themis AI was founded in 2021, originating from Dr. Daniela Rose's lab at MIT Computer Science and Artificial Intelligence Laboratory. Today, Themis AI is working with enterprises in a variety of industries, and many of those companies are building large language models by using Capsa, These models are able to quantify their own uncertainty from each output. If you would like to learn more about Themis AI, feel free to click the link in here. So how do we get there? We start with a simple but deep question. What is knowledge in AI? An AI's knowledge is stored in something called its feature space, a mathematical map of everything the model has learned. When the model sends input, a sentence, an image, a question, it transforms it into a vector, which becomes a point in this space. If two inputs mean similar things, their vectors are mathematically close. If they mean very different things, they are far apart. The model doesn't reason like a human. Instead, it checks, where does this input land in my feature space? If it lands in a familiar cluster, the model is confident. If it's far away or isolate in the space, the model is uncertain. It hasn't seen anything like it before. This is how the model understands relationships, not by logic, but by spatial similarity. This spatial distance becomes a powerful signal. The farther an input is from knowledge, the less confident the model should be. That's where Capsa comes in. Capsa is a light wrapper that monitors a model's internal behavior during prediction, without needing access to the training data. It doesn't change the model. Instead, it watches how the model reacts internally to each new input. Think of it like a second pair of eyes sitting outside of the model, but interpreting what's going on inside. Capsa looks at the model's internal elements and uses them to calculate risk metrics, and then to evaluate how far the model is from safe ground. Finally, Capsa maps those risk matrices into specific uncertainty types, giving developers and systems a clear, interpretable view of how reliable a prediction actually is. So, how Capsa reads internal signals? Capsa watches four key internal elements. First, embeddings. Interpreters are transformed into vectors, points in feature space. If the point is near no regions, confidence is high. If it's far away, uncertainty increases. Activations. Neurons fire as data flows through the network. Familiar inputs trigger focused strong activation patterns. Unfamiliar ones trigger scattered weak responses. Third, logits. These are raw prediction scores before softmax. If the scores all close together, the model is unsure. If one clear out stand out, it's confident. Finally, the softmax scores. These are final confidence values. High scores sound reasoning because they can deceptive if the input is unfamiliar. The softmax scores always sum to 100%, so even without confidence, the probabilities might be very high, shows the model is confident. Even the model might be confidently wrong. So actually these signals indicatedly reveal how the model perception the input in its feature space, even without showing the full map or assessing the training data set. In the last stage, Capsa maps those risk matrices into specific uncertainty. Capsa doesn't just collect numbers, it computes risk matrices like feature space distance, measure how far the input is from the model's learned knowledge, and confidence drop across layers. If confidence starts high but drops toward the end, it suggests the model gets confused the deeper it processes the input. Variance across similar inputs measures how much the model's prediction fluctuate when given inputs that are slightly different. Activation spread and concentration. If the activations are scattered and weak, it's a red flag. The model isn't recognizing a clear pattern. But if the activations are focused and strong, that's a signal the model is confident and familiar with what it's seeing. Then, Capsa performs something called uncertainty signature mapping, turning those patterns into recognizable type of uncertainty. Let's break those down. Aleatoric uncertainty. Aleatoric uncertainty comes from noisy, ambiguous, or overlapping data. Even with perfect training, some inputs are just hard to predict. It's like driving in fog. Even if you're a great driver, the road is blurry. It can't be eliminated by adding more training data because the uncertainty is part of the data. Instead, the model shows up as wild activation spread. The model lights up lots of areas because it's not sure what path the input matches. The uncertainty often can't fixed with more data. Not just because of the input data, it might caused by the training data. It's like training the model with blurry data, so the answer might or with some blurry content. The second one is epistemic uncertainty. Epistemic uncertainty happens when the model slightly hasn't learned enough. The input lands in a sparse or quiet area of the feature space. It's like being a map maker asked to chart a part of the forest you've never visited. You can guess with your experience, but you are not confident. This uncertainty can be improved with targeted retraining by adding more data in the underrepresented area. Capsa flags those gaps so teams know where the model's knowledge ends. It's just like this picture. The node clusters ground in here, but the input is a long distance from the core knowledge clusters, so it might need some data to fix from here. The last uncertainty is vacuitic uncertainty. Vacuitic uncertainty is totally unfamiliarity. The input is so different it doesn't even fit into the model's universe, which means the model not just guessing, it's completely lost. It's purely guessing what's going on. The model has no idea about the input data. It's like someone hands you a photo of the ocean and asks where it is on your forest map. You are completely lost. This uncertainty caused the model responses confidently to something it's never seen before. Capsa detects this but can't fix it without entirely new data. It's similar with epistemic uncertainty. It's just the point not have a distance with the core knowledge clusters. It's far away, even not on the picture. You couldn't see the red point in this picture, but it actually exists like out of the picture. So after Capsa detect those uncertainty, it's not where Capsa ends its job. Actually, Capsa could help to improve AI reliability. How does it get to there? Capsa improves AI reliability by identifying when the model is unsure and flagging those uncertainty responses before they are acted on. It not just give a simple answer. It gave some explain about why this model has this prediction. In traditional model, just one prediction, no insight. But with Capsa, there will have the uncertainty flag and explanation recognition. So you will know if this response could be trust and what caused this result, and how can you do to improve this AI model. This not just improve the reliability of AI model, it also improve transparency for users and systems. It allows software, not just humans, to handle responses differently based on confidence. For example, in low-risk cases, AI can act autonomously. In high-risk ones, it can ask for help or escalate. For users, this builds trust. They can see which answers are solid and which are risky. For systems, it enables smarter decisions, ruling uncertain cases for review, to take safe actions only when confidence is high. Capsa turns AI from a black box into a readable system. And also, Capsa not just identify and flag the uncertain responses, it also supports training optimization. It helps reduce epistemic uncertainty, which is the only one uncertainty that Capsa could to deal with. By smarter training to reduce epistemic uncertainty. Capsa helps reduce epistemic uncertainty by prioritize those challenging examples during training, ensuring the model pay more attention to them. And there is another way Capsa will do. Generate new similar data samples. In cases where certain regions of the data are underrepresented, Capsa can synthesize new data points to rebalance the training state. This kind of smarter targeted training reduces epistemic uncertainty, and that leads to better accuracy and stronger robustness in real-world scenarios. This is a code sample of using Capsa. We can say you can use only several lines of code to wrap the existing model and retraining with the training data. Also, we can say there is a function that will respond with the risk information from prediction of the existing model. You could also say the inside model. And also, Capsa do not just limited for language models. It works in image recognition too. In one test, a self-driving AI had never seen a deer during training, so it failed to recognize it on the road. We can see this is the input. There is a deer on the right, but in the prediction, there we can't see there is a deer. But in the Capsa risk result, there clearly see a shape that like a deer. So Capsa flagged the image as a high uncertainty, signaling that the model was out of its depth. In real-world environments like autonomous driving, the number of things an AI model might encounter is virtually unlimited, but the number of things it has been trained to recognize is always limited. That kind of warning is crucial in safety-critical systems. Even if the model can't name the object, knowing that it's unsure is enough to trigger fallback logic. That's how you go from black box guessing to engineered safety. Capsa is like a unit test for AI models. It doesn't change the model, it validates its knowledge coverage. Capsa doesn't change the model or rewrite its predictions. What it really does is review the blind spots, the places where the model is likely to fail. It looks inside the model and shows you where its knowledge is seen, where it's making guesses, and where it's never seen anything like this before. You can think of it like a flashlight in a dark room. It doesn't fix the room, but it shows you exactly where the corners are. That's powerful because once you know where the model struggles, you can do something about it. You can improve the training, rebalance the data, or change how the model is used in the real world. Capsa doesn't just help end users. It also gives risk signals to both developers and automated systems. For developers, it shows where the model lacks knowledge or makes unstable decisions, so they know where to force retraining or data connection. And for systems, Capsa provides real-time signals that say, hey, this response might not be reliable. That makes it possible to automatically route risk cases to humans, fallbacks, or safer logic. Instead of training all predictions the same, systems can now respond based on confidence, acting quick on low-risk inputs and being cautious with the ones that matter most. It's like giving both engineers and machines a built-in nearly warning system. Capsa brings something that's been missing from a lot of AI development: rigor. It helps turn AI from a black box guessing game into a measurable, testable, and accountable system, more like traditional software engineering. Just like unit tests or coverage reports in code, Capsa shows you what the model knows, where it's weak, and how reliable each output is. This changes the way teams build the AI. They are not just aiming for high accuracy anymore. They are measuring risk, reliability, and trust. It's a shift from experimenting in dark to engineering with clarity. And in serious business, safety, or scientific applications, that kind of rigor isn't optional. It's essential. Capsa does not assess truth. It assesses familiarity and concentrity based on the model's own learned feature space. It's important to understand one of Capsa's key limitations. Capsa doesn't know whether a prediction is actually correct or not. It just checks how familiar and confident the model is. If the model was trained on flawed data, it might still feel very certain, and the Capsa would flag that response as reliable because it matches the model's internal knowledge, even if the knowledge is wrong. In that way, Capsa works more like a unit test. It doesn't test if the output is right. It checks if the logic was followed based on what the system knows. So, while it's a powerful tool for measuring confidence and detecting uncertainty, it's not a truth checker. It reflects what the model knows, not what objectively. This picture from the screen of a video in Themis AI website. It shows one of the important limitations that Capsa has. We can see this question: what's the biggest US city that's only one word? The answer is Chicago. We all know it's the correct answer, but it's flagged in red because Capsa thinks it's uncertainty. Why? Because there are another word that has higher logit than Chicago. So this case shows a very clear picture that Capsa only compares the input with the model's internal knowledge. Stage of the AI life cycle. In development, it reveals knowledge gaps to teams can retrain. Instead of guessing where the model needs improvement, developers can target the right areas during retraining or data connection. It's a huge upgrade from tree and error. Now you are building AI with visibility. In testing, it simulates real-world unknowns and diagnoses how the model responds. Instead of just running static test cases and checking pass or fail, Capsa evaluates how the model behaves under unfamiliar edge case or risk inputs, just like what it might face in the real world. That shifts AI testing from being a checkbox to a true risk evaluation, making sure models aren't just accurate, but also aware of their own limits. In deployment, it routes uncertain predictions to the cloud for deeper analysis or human review, while allowing confident predictions to stay local. Training AI is expensive. It happens in powerful, centralized environments, but the prediction must be fast and lightweight, often running on edge diverse and with limited resources. Capsa helps bridge that gap. It wraps around the deployed model and flags inputs that seem unfamiliar or risky. When that happens, the model can route the input to the cloud for stronger models, retraining, or even human review. It even introduces a new concept, test coverage for AI. Just like software engineering targets how much the code is tested, Capsa tracks how much of the model's knowledge is exercised in the real world. In my view, the future demand of AI, not just smart, also need to be safe, measurable, and trustworthy. Today, AI models are measured by accuracy, parameter count, and latency, but none of those metrics answer the real question: can I trust this model when it's making decisions in the real world? Capsa adds that missing metric, reliability. It doesn't just measure what a model predicts. It tells you how well the model understands what it's doing. What's the foundation for credible, transparent, and trustworthy AI? A new standard for AI reliability. It gives AI models a way to show not just what they predict, but how confidently and responsibly they make those predictions. Just like accuracy and F1 became standard metrics in AI performance, Capsa's uncertainty and reliability in science can become the next essential scorecard, one that tells teams, users, and regulators whether a model is safe to trust. It's not just an improvement, it's a new category of standard for the new era of AI. Thanks for watching today's tech seminar. Let me know which part of the Capsa story catch your attention most, and how you see this changing in the future of AI. If this helped you think deeper about tech, give it a like and subscribe. I will see you in the next one.